Bayes' rule is something we've seen implicitly, but the probability of E1 given E2 in boldface there is the probability of E2 given E1 times the probability of E1 divided by E2. And this is important because in situations, experts may have ways of reliably giving you some probabilities and not others. And so it's important to be able to sort of flip the conditionality, if you will, in some situations. Essentially what I've shown here is that in that bold-faced comment, the probability of E1 given E2, you can express that in terms of the opposite conditional probability of E2 given E1 times the in this case times the probability of E1 in particular. This numerator, the probability of E2 given E1 times the probability of E1, gives you a joint probability of E1, probability of E1 and E2. And it's that joint probability that's the, I'll illustrate, is sort of the intermediate step in obtaining Bayes' rule. So in this middle part of the slide, we consider a diagnostician and who's building a diagnostic system, and the diagnostic system is going to be responsible for estimating the probability of a disease condition given a particular symptom, S sub j, estimate the probability of D sub I given S sub j. And the expert that we're relying on filling in these various diagnostic values, we might be able to estimate these objectively from sufficient data, but we might also rely on an expert to give us a judgment. May be very poor, and it turns out that human experts are relatively poor at estimating, in this case, disease outcomes from symptoms. What they're much better at is estimating symptoms, probability of symptoms given disease conditions. They're better at doing that. And so we would like to take this probability of disease given a symptom and translate it into an expression that involves the probability of a symptom given a disease. And that's what you see down there. And now the expert is, most experts are much better able to give us relatively accurate estimates of symptoms given diseases than the inverse. So, and this is kind of common. It's not just diseases per se in a medical application, but where I've talked about diseases here, we're talking about perhaps causal conditions. In this case, the disease causes a symptom, but there are many situations in which the some outcome, like a disease, is going to cause the symptoms. And it's typically easier to give a probability, an expert to give a estimated probability for something which is caused by something else rather than the inverse. It turns out that estimating the probabilities of symptoms all by themselves can be difficult for experts. But if you remember that point we made in talking about the Bayesian classifier, we may not actually have to explicitly model the unconditioned probability of the symptoms because the probability of the disease given the symptoms there, and I'm showing that at the bottom, is going to be, I can compute the probability of the individual diseases D1 through DM, and I'm actually on the next slide now. Let's see what number it is. Looks like it's slide 17. but I don't need to compute the numerator, or rather the denominator of these various ratios explicitly to know which the most probable is. So the probability of disease 1 given symptom J is proportional to the probability of symptom J given disease 1 times the probability of disease 1. And I don't need to divide that by the probability of the symptom per se, because the probability of the symptom is going to be true for all those possible diseases. So I don't need it to tell me which is the most probable disease outcome. Going to slide 18 now, the chain rule. We saw the chain rule in talking about the naive Bayesian classifier. At the bottom is sort of what you saw last time, and I'm simply going to, given that we've talked about it at some depth, I'm going to go to the next slide, or slide 19, where we can put the chain rule and Bayes rule together. You can study this rewriting later, but the first step is the application of Bayes rule, where the probability of disease given a whole set of symptoms is equal to the probability of the set of symptoms given the disease times the probability of the disease divided by the probability of the symptoms individually. And then we can apply the chain rule that gives us this next step. So the probability above, after applying Bayes' rule, can be rewritten as probability of disease times a probability of a symptom given a disease, and we build out, using the chain rule, the conditioning information that's given. And study this later. It's interesting and important, but what it allows us to do in particular is it allows us to do what's called Bayesian updating. So if you take a look at this bottom slide, or this bottom formula, or rather bottom expression on slide 19, proportional, all this stuff above is proportional to the probability of the disease times the probability of the symptom given the disease, times the probability of another symptom given the disease and the first symptom, et cetera, et cetera, et cetera, is this expression allows us to revise our estimates of the probability as we gather more evidence. So if you haven't seen any evidence and you're trying to make a prediction about what the most likely disease is of someone that walks in the door, all you have available is the probability of the diseases themselves to rank what diseases might apply to this new patient. When you collect your first piece of evidence, which is, say, S1, the value of S1, which might be a lab test, for example, or just stemming from a visual inspection, you now have probability of the disease times the probability of S1 given the disease. And that's a revised estimate of something proportional to the probability of disease 1. And you've got a revised estimate at that point of the probability for disease 2 and disease 3 and disease 4. And so you can make, if that's all you've got to go on, that one piece of evidence, then you can pick the most probable at that point. But if symptom 2 now comes in, you can do a further revision of all your disease probabilities and make a better judgment. And then the next symptom come up in, et cetera. So this chain rule in this particular diagnostic example allows you to make incremental revisions on your estimates of probabilities, so that at any point in time you can say this is the most probable outcome given the evidence I've got, but if new evidence comes in or more evidence comes in, I can revise that. Slide 20 now. At the top it says, where do these probabilities come from? They might come from a whole bunch of data that you've collected and you give objective judgments. It would be hard to imagine that if you've got many symptoms that you are concerned with, that experts would be equipped to come up with subjective judgments about these probabilities with lots of conditioning information on the right-hand side of the vertical bar. But what we can often do is we can make independence assumptions. And when we talked about the naive Bayesian classifier, we made a rather radical independence assumption. But in general, we can make more nuanced independence assumptions. At the bottom here, I've got the probability of two outcomes, W sub I and W sub J. I've expressed those as a conditional probability of one given the other times the probability of the other. And if these two outcomes, though, are independent, then we can rewrite the joint probability as the probability of one outcome W sub I times the probability of the outcome W sub J. And this is one definition of independence amongst two variables, but it has some equivalent definitions. Perhaps the ones that are most intuitive here are shown. Independence can also be defined. These are all equivalent definitions. Each implies the other. The probability of one outcome given the other simply equals the probability of one outcome, W sub I in this case. That is, knowing what the value of W sub J is, knowing W sub J gives you no additional information as to the probability of W sub I. So there's no advantage to knowing W sub J. It doesn't revise your prediction or the probability of W sub J. And that's a nice intuitive explanation. I'm going to skip now to have a look at slide 21. We spent a fair amount of time when we talked about the naive Bayesian classifier talking about conditional independence. On slide 22, again, just another illustration that is in a diagnostic domain that's akin to something we've talked about. So I'm going to go review a slide that we talked about in